Welcome to This Explainer, where we're going to pit two heavyweight sorting algorithms against each other to see exactly how they quietly organize our digital world. Think about it. Every single day, whether you're filtering a massive spreadsheet, searching through a massive database, or just, organizing your music library by artist, there's an invisible engine running in the background, making it happen instantly. So today, we're pulling back the curtain on two of the absolute most powerful engines in computer science, merge sort and quicksort.
Here's our game plan for this explainer. First, we'll look at the divide and conquer strategy, then move into understanding merge sort, followed by understanding quicksort. After that, we'll get into the art of the pivot, run a head-to-head performance complexity showdown, and wrap up with real-world best use cases. Let's just jump right in.
All right, starting with Section 1, the divide and conquer strategy, the shared DNA between these two algorithms.
So both of these algorithms actually attack a problem using what's called a divide and conquer approach. Basically, this means taking a massive problem, breaking it down into similar, smaller subproblems, solving those recursively, and then combining the solutions. It's all about taking a huge data sorting problem, chopping it into smaller, manageable bite-sized pieces, solving those, and then seamlessly putting them all back together. Instead of looking at a list of, say, 1 million items and panicking, the algorithm essentially says, well, let's just look at 500,000. Actually, scratch that. Let's keep having it until we're only looking at a few items at a time. It is incredibly elegant when you really think about it.
Moving on to Section 2, understanding merge sort. We like to call this one the predictable heavyweight.
So merge sort methodically splits an unsorted array perfectly in half, again and again, until only single elements remain. And since an array of just one item is, by definition, already sorted, the real magic here happens in the combine step. It compares these tiny individual arrays, merges them into slightly larger sorted arrays, and just repeats this process all the way back up until the entire list is combined into perfect sorted order.
But there's always a catch, right? There is a specific cost to this super methodical approach. The absolutely crucial point to remember here is that merge sort is an external algorithm. That means it requires additional memory space, an auxiliary array, to safely hold the data as it merges it back together. It doesn't do all this sorting in the original space you provided. It needs a workspace. It literally sets up extra arrays to hold the left and right halves temporarily while it figures out exactly which element comes next.
Okay, let's pivot to Section 3, understanding quicksort, our agile challenger.
Quicksort tackles the exact same problem, but totally differently. It identifies a target element, which we call a pivot. It then moves all the smaller items to the left of this pivot and all the larger items to its right, which places the pivot in its exact final sorted position. And the cool part? It does this partitioning right there in the original array. Once that pivot is locked in place, it recursively applies the exact same steps to the subarray on the left and the subarray on the right.
Which brings us to Section 4, the art of the pivot, where strategy is pretty much everything.
Quicksort's true secret weapon, and honestly its biggest potential risk, lies entirely in how it chooses that pivot element. Engineers have spent years developing different strategies to pick the best one. For example, the Lumito partition is simple. You just grab the last element. But if your data is already mostly sorted, this choice actually cripples the algorithm's speed. To counter that, we have randomized pivot selection, which just picks an element completely at random. Then there's the median of 3 strategy, which looks at the first, middle, and last elements and picks the middle value. That is a fantastic way to avoid bad splits. And then, for sure, there is the highly advanced dual pivot approach. This actually uses 2 pivots to chunk the data into 3 distinct sections, making the entire sorting process incredibly fast. All right, it is time for Section 5, head-to-head performance complexity, the ultimate showdown.
When we evaluate average time complexity, both of these algorithms excel at a big O of n log n. This basically means they're both incredibly efficient for large datasets on average. But the real divergence happens in the extreme edge cases and the physical memory they use. Quicksort risks a much slower big O of n squared time if it hits a totally terrible pivot, while merge sort is perfectly consistent but eats up far more physical memory. Merge sort requires big O of n space because of that extra auxiliary workspace we talked about earlier. Quicksort, it only requires big O of log n space for its recursion stack. Because quicksort operates in place, its cache behavior is absolutely fantastic. It's working with memory addresses that are right next to each other, which modern computer processors absolutely love. Merge sort's cache behavior, on the other hand, is relatively poor because it is constantly bouncing data back and forth to that auxiliary array.
Now, you might hear that worst case time for quicksort and think, well, that's a total deal breaker.
But here is the pro tip. Using a randomized pivot for quicksort drastically reduces the chance of that dreaded worst-case scenario, making it incredibly fast in practice. By just introducing a little bit of randomness into how we pick the pivot, the statistical probability of repeatedly picking the absolute worst pivot drops to almost zero.
So, Section 6, Real-World Best Use Cases. Time for the final verdict. Quicksort is the undisputed champ for standard in-memory arrays, entirely due to its cache locality. Meanwhile, merge sort takes the crown when you're sorting linked lists or when you absolutely need what's called a stable sort to preserve original element ordering. If you are sorting a standard array of numbers, quicksort's cache friendliness makes it the clear winner. But merge sort has this incredible superpower. It's a stable sort. Imagine you're sorting a list of employees by their department, and then you sort that same list again by their age. Merge sort guarantees that employees within the same age group will remain grouped by their department. Quicksort simply cannot guarantee that original order. Furthermore, if you happen to be sorting linked lists rather than arrays, merge sort is totally ideal because linked list can be split just by changing pointers, effectively eliminating merge sort's usual heavy memory penalty.
Every single time you hit sort, an algorithm is making rapid-fire decisions, constantly balancing time against space and stability against cache efficiency. Thanks so much for diving into this explainer with me. So the next time your digital world seamlessly organizes itself, take a second to consider the brilliant, invisible engineering choices happening entirely in the background. Next time you sort a massive spreadsheet, ask yourself, which hidden algorithm is secretly balancing speed against your computer's memory to give you the absolute